Hello. Good morning, ladies and gentlemen. Uh, I welcome you all to the first session of today's morning. Our first speaker is Professor Feng from the Department of Mathematics, UC Riverside, and he will be talking about the entropies in quantum field theory. Let's welcome him to give us.
All right, so I'd like to thank the organizers for inviting me. So I've been talking about entropies in quantum field theory. I have that subject that I've been working for the last few years. Um, so um, the entropy, of course, is a subject with a long history, and it plays a very important role in quantum mechanics. What got me excited in the last few years is that previously most of these work is about a finite dimensional system in some sense, but with finite degrees of freedom. But in quantum field theory, the infinite degrees of freedom, so mathematically it gets more exciting from my point of view. So I'd like to tell you a few results in this direction. But first, maybe I'll stick with the uh, slides. So here's some motivations and results. So I've already mentioned that entanglement is one of the most intricate aspects of quantum mechanics. Von Neumann entropy is a mathematical concept that can be used to measure entanglement. Okay, and this concept, this generalizations have been discussed extensively. Okay, in literature related to questions about entanglement. In the last few years, there have been enormous amount of work by physicists concerning entanglement entropies in quantum field theory. There's various motivations. Okay, so here's the attractive slogan I've learned from my physics friends. So entanglement is the glue of space-time, and gravity is the hydrodynamics of entanglement. Okay, whatever that means. Okay, but it's very attractive, and um, my goal is to actually to see if there's some interesting mathematical results coming uh, from this. Okay, so I'd like to convince you that there's some interesting mathematical questions. For instance, when the entropy is computed in physics literature usually infinite. This is because for type 3 factors, which always arise in QFT, the non entropy is always infinite. Okay. The mutual information, however, is argued to be finite, okay, based on some heuristic arguments. And one can usually derive the singularities of the entropies from the mutual information by taking some kind of singular limits. Okay, I'll make this precise uh, in the next 20 minutes or so. Okay, but it's not been clear that such mutual information, which is well defined as a special case of Araki's relative entropy, which I will recall in the next few slides, is infinite. So our work sort of address some of these questions. So I think that these are fundamental questions before you even talk about the applications of these entropies. Okay, so you have some quantity, is it finite? It's very, very simple, simple-minded question. Okay. All right. So our work is sort of motivated by Ed Wheaton's questions, in particular his questions to make these computations rigorous. So I'd like to report a few results in this direction. So the first result is that we have exact computation of mutual information through the relative entropy defined by Araki for general states of non entropy. So this is done for free fermions, okay, the CAR algebras, okay. Um, I'll tell you what the result is. So this was not even known to be finite, okay, before our work. So our proof use various things. So first, there's Luke's convexity in solution to the Riemann-Hilbert problem on intervals on the real line. Okay. So to the best of knowledge, these unrelated results are the first such relative entropies that are computed in a mathematical rigorous way. Okay? So I just want to give you a taste of one such result. For instance, if you take what's called chiral-free net, I will actually define this later. So these are some kind of mathematical description of chiral conformal field theory. And if you take two intervals on the real line, so these two intervals are disjoint from each other, so B1 is less than A2, then the mutual information associated with these two intervals, I will define this later. So this is some kind of Araki's relative entropy is given by this formula. So it's minus R over 6. times logarithm of eta. So where eta is the cross ratio. Okay, so so this is an exact result. So before that, we don't even know this relative entropy is finite or not. So now we have exact formula. Okay, so it's often this happens often in mathematics. Once you have exact formula, you expect a lot of interesting applications. Before I say anything about it, you may wonder, for those of you who know what this caret CFD is, these are fermions, these are free series, right? What's the big deal of computing relative entropy in such a free theory? Okay, for free theory, there are no mathematical problems, right? Unlike the million-dollar question, the Yang-Mills theory, they're interactive theories, right? So what's the big deal of computing relative entropy in such a framework? Well, that's because of the magic of relative entropy, because it has various interesting properties. So for instance, it has a monotonic property. So it follows immediately from our result, from the free theory result, free theory computation, that any CFT, in fact, any CFT that can be embedded in the free fermions and finite index extension, never mind about that. I will define index later. They will all have finite mutual information. Okay? Simply because of the monotonicity of relative entropy. So if it embeds, then it gets smaller. So we immediately show that all these CFT have finite mutual information. Okay? So that's the first consequence. So as I said, this includes large family of CFT. In fact, all the known ones, the ones we're interested in. In fact, many of us have studied for many years, for instance. And also, a theorem connects relative entropy index of subvectors in a sort of interesting or unexpected way. But this connection is different from the Pipson and Popper result that connects Cohn-Stromer entropy to index. We'll see that in a minute, okay, in the next 20 minutes or so. There's also a bit of surprise when we proved this. We actually didn't expect this, but then we find that vacuum stable complementary regions in fact have a different relative entropy, and the violation turns out to be measured by global index. You'll see a bit about this later. Okay. So that's a sort of consequence of our computation of relative entropy in a free theory. Okay, because of the special nature of CFD, then it passes immediately to sub-ones. Okay, so you get a lot of so for instance, the WZW model, this is the one that everybody in CFD loves, and it follows all of them have finite mutual information. So that's a consequence of a first result. All right, so yeah, so let me, I should just stay with the slides, okay? So the violation in some sense the logarithm of the global index, which turns out to be what's called the topological entanglement entropy, okay? Anyway, in addition, we also proved the exact formula for singular limits of relative entropy in the two-dimensional massive free fermion case. Okay, this formula was sort of predicted by Cassini and Buruta, and based on heuristic path integral arguments, okay, which are very difficult, if not impossible, to justify, and also by the discussions on C theorems. Okay, so proofs are quite non-trivial and really rely on deep theory of SJM about homomorphic CF quantum fields in 1970s. Okay, and our recent work on entropy estimation. Okay, I think that's all I want to say about the motivation and results. So let me see. Yeah, so that's the motivation and results. So at least you get an idea what the results we have proved in the last few years. Okay. So I'm going to sort of give you a gentle introduction, and I want to define the entropy, relative entropy, and also the concept of mutual information and so forth. Okay, so in other words, the terminology I haven't explained in the previous section about motivation results hopefully will be explained in the next uh, uh, half an hour or so. Okay, so let me see. There's no clock in this room, so I need to maybe I'll get my phone out. Okay. All right. So here's a gentle introduction to entropy, relative entropy, and index for subvectors. I think most of you probably know this, but let's start with some things very elementary. So if I have a probability function of finite set, okay, the Shannon's information entropy is defined to be this. is minus pi log pi. Okay. So you can see that this entropy is greater or equal to 0, like let's equal logarithm n, and it can be thought as a measurement of uncertainty in p, because this attains its maximum value and when n outcomes are equal likely. Okay, and it reaches its minimum value if it's definite, right? If certain event happens with probability of 1. Okay, so this channel's entropy can be thought as measurement of uncertainty. Okay. So according to, this is what I find out on the internet. Okay, so according to Claude Shannon, the phenomenon gives him very useful advice on what to call its measure of information content. You should call it entropy, and then nobody really knows what entropy really is, and so in the debate you always have the advantage. Okay? So anyway, but in fact, I think von Neumann was joking because 2 decades before Shannon, von Neumann defined what's now known as von Neumann entropy. Okay, it's likely. Now, when I told people about this, somebody mentioned that it's likely von Neumann was inspired by work done by Boltzmann entropy. Okay, so the list of related work might be too long to be included in this talk. Okay, so instead I would just define what's entropy, what's von Neumann's entropy. Okay, so here's von Neumann entropy is the quantity associated with a density matrix. So a density matrix is a positive trace class operator on Hughes with trace equal to 1. Okay, this is the non-commutative version of the probability measure. Okay, so this is von Neumann entropy. It's minus trace rho log. Okay, and similarly, it can be thought as a measure of likely information about the system to which one will strip the state. So, for instance, S rho is greater or equal to 0, and for a pure state, it has vanishing von Neumann entropy, and it gets its maximum value if rho is 1 over n times the identity matrix. Okay, and it's the dimension of the Hilbert space. In that case, S rho is log n. Okay, so one thing I like to point out is that von Neumann entropy is non-linear in the state, and in general, it's because of these log rho part, right? So it's not easy to compute even in a finite dimensional case, such as those that arise in statistical mechanical system. Okay, even in that case, finding these it's not I mean it's not easy. I mean in literature there are actually lots of computations, right, of these entropy on the lattices and so forth. Okay. Anyway, so it's also clear that the estimation of entropy will rely on the Shannon von Neumann class for p greater than 0, less than 1, right? Because of this logarithm term. Okay. So this is not a Banach space in general. Okay, and it's less discussed in the literature compared to p greater than equal to 1 case. Okay, so this is like LP space for p greater than 0, less than 1. Okay? Anyway, so that's just a technical remark. So that's von Neumann entropy. So I sort of mentioned earlier that one thing about von Neumann entropy is it doesn't generalize to general situation. Okay, but there's a related notion of entropy called the relative entropy. So it's defined in the for two density matrices by these formula. Okay, so now we got two density matrices, and this is the relative entropy. So like entropy, relative entropy is non-negative, but it can be infinite. Okay, and it can think of these relative entropy as sort of measure the distance between two density matrices. Okay, because it's always greater or equal to 0. Okay, but not quite, because you can see that these relative entropy are not symmetrical in rho and rho prime. Okay, so it's not a distance function, but some people just symmetrize this to get a distance function. Okay, there's some people using this relative entropy, symmetrized relative entropy, to actually measure the distance between the states. Okay. So, like I said earlier, like von Neumann entropy, generalization of relative entropy in the context of von Neumann algebras of arbitrary type is possible, and this was found by Araki in the 1970s or maybe late 1960s. So for those, but this have to use modular theory. So the next slide or two, I just want to give you an idea what this Araki's relative entropy is. Okay, just to give you a definition of Araki's relative entropy. In other words, there's a definition. Okay, but I'm actually not going to make much use of it. So here's the official definition. You take two faithful normal states on normal algebra A in the standard form. You choose the vector representation as the natural cone on this standard representation, you have two representative corresponding to these two vectors, and then you define what's called the relative modular operator. So if omega is the same as omega prime, this is the usual modular operator. Okay, and then you take the polar decomposition. Um, sorry, this is the S operator, and the polar decomposition you have the corresponding relative modular operator. Okay, so in the physics literature, this is what's known as modular Hamiltonian. Okay. All right, so what's the relative entropy in this case? Well, just this logarithm of these relative modular operator, the expectation of these logarithm relative modular operator on this state omega corresponding to is the vector representative of omega here. Okay, and this can be extended to positive linear function in general, not just states. Right? In the usual way. So I'm just throwing out this formula there just to, just to show you that there is a definition, okay? And it's defined for any states on any phenomenon, okay? All right, so maybe I will, maybe I will just show you that in the type 1 case, if your underlying algebra is B of H, that definition recovers the relative entropy I defined before. So for instance, if you have type 1 polynomial algebra, the density matrices will be given by, the states will be given by these density matrices, right? So you work out the modular operator, you work out this formula, you get exactly the relative entropy for density matrices I have defined earlier. Okay, so this is indeed a generalization. Okay. All right. So as another example, so these examples are very important examples in quantum information theory, for instance. So if you take a bipartite system, you take a state on this bipartite system, you have a density matrix which is denoted by rho AB, and then you trace over, for instance, HB here. So these physicists write a trace over. You can think of this as expectation value, conditional expectation from A to B and J. Okay, so if you do that, you get another what's called the reduced density matrix, which defines a state on this first factor, and similarly for system B, and you work out what's called the mutual information. So I have said mutual information a couple of times. This is a special case of relative entropy. So in this case, there are two states on this A. One is rho AB, that's given, and rho A tensor rho B, these are given by tracing out the first factor and the second factor and take the tensor product. Okay, so that gives also a state on A, and the relative entropy in this case is what's called the mutual information, and it turns out to be related to von Neumann entropy. Okay, so it's given by this formula is the von Neumann entropy of rho A, von Neumann entropy of rho B minus the von Neumann entropy of rho AB. Okay, all right, so similarly, if you have a tripartite system, you can do exactly the same thing. Hopefully, these notations are clear. So, for instance, rho AB is the state rho ABC, on a tripartite system, but traced over C, you're left with a density matrix on A tensor B, right? So these you get these von Neumann entropies if you work out the corresponding mutual information using the fact that this mutual information is greater equal to 0 and is monotonic, you get what's called a strong subadditivity condition. Okay, this plays a very important role in the quantum information theory, for instance. Okay, so as I said, this was originally, well, I didn't say this, but it was originally proved by Liu and Rusky, but it actually follows rather easily from monotonicity of relative entropy, which I will talk about in a bit. Okay? So the message here is the following. Okay, so what's the interest in relative entropy? Even if you just care about von Neumann entropy, so by using the properties of relative entropy, you can prove some interesting properties of von Neumann entropies, right? Even if you're just interested in von Neumann entropy alone, it turns out that this relative entropy is surprisingly useful. So, for instance, an equality like this originally was proved by very hard analysis, but now it follows rather easily. Okay, from the monotonicity of relative entropy, which I will recall in a minute. Okay, the second point I want to make is that the thing I have repeatedly emphasized that the relative entropy, unlike von Neumann entropy, is more general. It can be defined for any type of Neumann algorithms, right? This is extremely important for consideration quantum field theory. Okay? All right, so unlike the quantum mechanics, in quantum field theory, type 3 factors appear naturally. right? So this part is extremely important for later work. Okay. All right. So yeah. So let me recall some properties of relative entropy. So previously, I have defined relative entropy by using Araki's definition, right, in terms of relative modular operator. But now there is so what Kosaki discovered. It's another formula, which is it's amazing formula. So let's see. Right. So I have the dot here. So this is the Kosaki's formula. So this is Araki's relative entropy. Recall what I did before, right? You can forget about this now because of Kosaki's theorem. Kosaki proved that this is equal to the right-hand side. Very ugly looking formula, especially if you see this first time, right? So it's a variational formula. You got two sup here, okay? And m is a positive integer, xt and yt. Xt is a step function with value in m, which equals to 0 when it's sufficiently large. Okay, yt is 1 minus xt. So what's the expression here? It's logarithm of m minus integral from m inverse to infinity. So this is a cutoff from 0, right? And then there's the evaluation of these two states on the elements here. Omega xt star xt, 1 over t. Omega prime yt star 1 over t squared dt. Okay, so notice that this star in different place. For those of us working modular theory, you see there's some kind of modular operator here, right? And also notice that it's not symmetric as expected. Okay. All right. So one thing to notice about Araki's formula is that Kosaki's formula, sorry, it makes no reference to representations of this algebra, right? You don't have to choose a representative. It depends only on states, as it should be. Okay. And also, if you have a supercomputer, you can evaluate these relative entropy, right? You just well, I mean, all algebra is always infinite dimensional, but frequently they're approximately, I mean, they can be approximately finite dimensional algebras. So if you got a supercomputer, you can compute. Okay, just evaluate states on this, and also I should point out that these xt are step functions. So even though this is written as an integral, but this effectively is finite sum. Okay, so if you got a supercomputer, you can just compute. Okay, you don't have to know modular theory to do this. Okay, and also as you guys already see this, many properties of relative entropy follows easily from this formula. So for instance, if you got two normal states of mononomial algebra M, and if you got a subalgebra of M, so I denote by omega 1, phi 1, the restriction to this subalgebra, then it follows immediately that the relative entropy restricted subalgebra is going to be smaller, right? Why is that? Let's look at the variation formula. If you compute the relative entropy on a smaller algebra, you're souping over a smaller set, okay? Therefore, it's smaller. So the monotonicity, which I sort of emphasized at the very beginning, follows directly from this formula, okay? Another example, is what's called the martingale property. If you got an increasing sequence of mononomial subalgebra of M, so that this increasing sequence generates M, then these relative entropy converges. Okay, let's prove this. This is a first-year calculus problem. Let's prove this. Okay, so let's suppose we got an increasing sequence. I know this is an increasing sequence of positive numbers, right? It can be infinity. Okay, it's increasing. I want to show you increase to this number. Okay, so what do? I take this number, take an epsilon. Okay, this number is given by this variation formula. So after an error of epsilon, I can find some finite linear expressions here, so that it's close to these s omega omega prime after error epsilon. Okay, but then on this expression, which involves evaluation of omega omega prime on finite number of elements in M, because Mi increased into M in the weak sense, okay, and omega prime a normal state. So you can always find those when I is large enough, you can find those some Mn, so that those elements which appear in this expression can be approximated. It's extremely important. These are finite expressions, okay? Can be approximated up to error epsilon by those elements in Mn, right? And then we're done. Okay? So this is the martingale property. Okay? So this is what I like about Kosaki's formula. Okay? Initially, when I look at this, it's pretty hard to understand. But then, it's really great. I mean, all the properties are built in now, right? if you take this as a definition. But of course, this is not very illuminating. Okay? So another thing I like about this is I actually made use of this. Okay, so later on when I estimate entropy using index, I actually use this formula. So I thought I would never be able to use such a thing because you got two soups there, right? But then magically, when you actually want to do some estimation, this formula comes handy. Okay. All right, so this is the relative entropy, and then I have to, if you look at this little title here, there's an index there. So I want to tell you a little bit. Okay, so yeah, so this is a comment I probably made earlier. So for type 3 factors, von Neumann entropy is always infinite, no matter how you define it. Okay, so physicists' understanding of this that if you have quantum field theorem on the boundary, you got infinite many tangled bare pairs. Okay, so the von Neumann entropy is always infinite. Okay, that's their explanation. It's not our explanation, but anyway, no matter how you define it, it's always infinite. Okay, but mutual information is finite. The relative entropy is finite. So and also you're not going to lose physics intuition by focusing on this relative entropy, because as I said, we explore later, if you consider the case of singularities, by this I mean you like two algebras getting closer to each other, you actually can explore the singularities. So my point of view is that relative entropy is more fundamental. Okay, you should take that as a fundamental concept, and all the other things you should be able to derive them. Okay, so this is the message here. Okay, all right. So let's see. Yeah, so just for those of you who have, I see most of you have seen subvectors before, but just for the students who have seen this before, so this is a subvector theory that was initiated by von Jones in the 80s and has a major impact on mathematical physics. So this is how subvector is defined. If you take a phenomenon vector and n is a subvector, it can define a dimension-like numerical invariant, okay, so called the Jones index. So these measures how many copies of n you need to put in the n, okay? But it's not always integer, so you should think of this as relative size of m and n. Okay, so for instance, one of the first things Jones proved is following. So this value, the Jones index takes value in the following set. So if the index is less than 4 is discrete, and then takes continuous values, right? Like the spectrum of hydrogen atom, okay, electrons hydrogen atom. Okay. Anyway, so the original definition was in the type 2-1 setting, and it was generalized arbitrary type by Kawasaki and Longo. So here, once again, I just recall what this definition is. You don't really have to know this, okay? But it's presented in terms of expectation value, and the index is defined to be the best constant, so that this inequality is verified. Okay? There are equivalent definitions of this, but I just this is famous inequality. I just want to throw in there. Okay, so there's a general theory about index for arbitrary factors. So I want to point out, what's relevant for our results is the immediate consequence of this inequality, the Poisson inequality is an estimation of relative entropy in terms of index. Okay, so here we got a state. Omega composed with E is another state because E is a conditional expectation. Okay, so if you measure the relative entropy between these two states, it's actually dominated by minus logarithm of the logarithm of the index. Okay, so anyway, so this is all I want to say about index of subvectors. Okay. All right, so let's see. Right, so now I want to talk about one of the exact results I mentioned earlier, the Carrier-Ford fermion. So I just want to define everything in this setting. You don't have to worry too much. It's a mathematical formulation of conformal field theory. So some of this might be familiar to some of you. So here's a Hilbert space. It's the square integrable summable CR valued function. Okay, and the group of LUR, these are smooth maps from the circle to unitary group on CR. And so access multiplication operators, you decompose this Hilbert space into the positive energy part and negative energy part in some sense, okay? And then there is a representation of, so then I guess I'm really interested in what's called the fermionic Fock space. So you take this as your one particle space, and then you take all the fermions building out of this. Okay, So never mind about these, seems like a partition this into two, right? This is what's called the direct C's construction, just to eliminate the negative energy spectrum, okay? So never mind about this. This is some fermion space, okay? So I'm going to define the CAR algebra now. Um, so this creates some Phenomenon algebra. So these A psi and A psi star, these are creation operators. So these are the usual CAR operators, okay? And then you take the C psi here. This is a self-adjoint operator. You take the Phenomenon algebra, it's generated by this, okay? And this generates what's called a net in the following sense. If you fix the interval I, you take these psi's which are localized on I. So these psi's are functions which, whose support is on interval I. You take these creation operators and they generate phenomenon algebra in some sense localized on this interval I. So these are sort of algebras of observables localized on interval I. Okay, so you take that, and these will give you so-called the net of R free fermions. Okay, so this is the sort of mathematical formulation of chiral CFT for the free fermion case. So this is going to be our algebra. So I told you what the algebra is. My goal is to compute some relative entropy, so I have to tell you what these two states are. Okay, the first state is what you yeah. So I have also discussed maybe before I do that. So right. So the mutual information we're going to compute is this one. Okay, so first we'll face two disjoint open intervals. Remember, my algebra is associated to intervals. So to specify the algebra, I have to tell you what the intervals are. So I take two disjoint intervals. Okay, omega is the vacuum state. So I forgot to mention that for these quantum field theory, there's always vacuum state, which is the state unique up to constant multiplication by constant, is the state with the lowest energy 0. Okay, so that's the vacuum state, and then omega 1 tensor omega 2. So these two here I will express. So this is a gradient tensor product, so that's why I put subscript 2 there. So omega 1 is the vacuum state restricted to AI1. Okay, omega 2 is the one associated with I2. And I'm computing the relative entropy between these two states. Okay, so I got my algebra associated to I1 and I2. I got two states, okay, on this algebra. So the goal is to compute this. Okay, so I want to give you a flavor of about how we go about computing this relative entropy. So to do that, it's more convenient to map the circle to the onto the real line, and then you can work out what these states are. So maybe I'll do it in the next page, and you find out what the Hardy space projection is, the usual Hilbert transform up to some up to a identity matrix. Okay, and then you work out the kernel here, and the states can actually be defined by using Hilbert transform to some extent. Okay, so I'm setting up the stage so that the next thing seems to be reasonable. So we define the quantity like this, okay, associated to any interval. So this is our first main result. Fortunately, this doesn't come out. But anyway, so this is the first main result. So this is a general result. So not just one, two disjoint intervals. I have multi-disjoint intervals. We can do exactly the same thing. So this is a computation of relative entropy for such general intervals. Okay, the result I mentioned at the very beginning is the case when there are only two disjoint intervals, and when this R is the number of free fermions. Okay, so I do that. I did the previous preparation of these Hilbert transform just to give you guys an idea that it's not surprising that the Riemann-Hilbert problem comes in this setting, right, for disjoint intervals, and also Loop's joint convexity is extremely important for us because we want to control the we basically prove this by finding dimensional approximation, but we need good control on the relative entropy, and that's provided by this joint convexity. But anyway, so I think this is an interesting result. Its proof itself is probably even more interesting, but this result is going to play a fundamental role. Okay, so that's the description of the first result, the exact computation of relative entropy in the free fermion case. Okay, so now I want to talk about an application of these results. Okay, so if you take any conformal net, okay, I didn't define that, but the previous fermion case is an example of a conformal net. And then we discussed these similar mutual information. So omega once again is the vacuum state. A and B are two subsystem. You take omega restricted to A, you get omega A, and then you also get omega B, you take the test product, right? So we consider this relative entropy, and then um, you from this you and the monotonicity, the various properties of relative entropy, immediately get lots of interesting results from this. So I want to mention one of them. This is interesting. It appears in my screen, but okay. But anyway, so so here's another theorem. So the part that's blackened out is theorem 2. But anyway, so we have theorem 2 here. Um, so here's the result about what I call the recovering things, the singularities from when you let algebras getting closer to each other. So here I got two intervals, A1, A2 epsilon, A2. So A2 epsilon is going to be very close to A2. Okay, so A2 epsilon minus A2 is the distance is epsilon now. I want to see how this relative entropy behaves when these two endpoints getting closer to each other. Okay? So if they're getting closer to each other, this is our result. So you got a logarithm divergence, which sort of expected on some physical grounds. And then you got something which is very interesting here. This is minus half logarithm mu b. Okay? Mu b is what's called the global index of conformal net, defined by Kawajikashi, Langdon, Muga, and there's an O epsilon term. Okay? So this is what I said before. This mutual information knows everything about the underlying system. Okay? We know for conformal net, these are very important quantity. And R is actually, in this case, is the central charge. Okay? So you can recover everything from this, not everything, I'm exaggerating, but lots of interesting characteristic quantities of your underlying conformal theory by just looking at mutual information. Okay? So this, this, I hope reaffirmed what I said before, that this is really a fundamental thing. It knows a lot of things about the underlying system, as it should be, right? Because it's supposed to be a very important quantity. Okay, so you recover the global index, you recover the central charge by looking at the singular limits. Okay. All right. So this is this. All right. So yeah, this is one more comment. The constant term is related to what's the topological entropy discussed, for example, by physicists like Kitaev and Pascal, and even with the right factor. Okay, so this is what I had before. So what I mean by this is this particular term, okay, minus half log mu. Physicists argue this by completely different things and very hand-waving. And to this day, I don't even understand, but I understand this result perfectly. Okay. But anyway, so okay, so I should also mention the duality. So I sort of there's a little bit of surprise in this case. So this slide is prepared to show you what the surprise is. Okay, so the surprise is this. So here I got the mutual information for A and B, these two underlying systems. This A, C, and B, C, never mind about the previous term. So I just want to make everything is precise here. So I just want to tell you what this thing is set up for. So I got AC and BC. So AC is the complement of A. BC is the complement of B. Okay? So there's an argument in physics literature that if you got a pure state, okay, the entropy, pure state, entropy has to be 0, right? So if you have A and A complement, then the phenomenon entropy for A and the phenomenon entropy for AC has to be the same. So if you go through that formal argument, you will see that the mutual information has to satisfy this property. Okay, and this property is equivalent to if you set up the cross ratio. So I should say that cross ratio. Let me see how much. So I got about 10 minutes, right? Okay, right. So the cross ratio here, the cross ratio. So I write in cross ratio. And never mind the cross ratio, because in this case things are conformal, so things only depend on cross ratio of these two intervals. That's why this all cross ratio. So this duality relation is equivalent to this relation here. Okay, so so we know that for free fermion you can check directly because we have the exact result I mentioned before. So you can check this is true. But however, we find that once the index is non-trivial, this is never true. Okay, so this sort of argument. So let's not worry about this argument. So as long as your underlying conformal net has non-trivial what's called the super selection structures, then the mutual information is never satisfy this duality. Okay? So this was a bit surprising to me, to us, right? So when we set out proving this, we try to prove this is equal because free fermion is equal. But then, we can't prove it, and finally we realize it's almost never equal. Okay? So what goes wrong with the formal argument? Okay, so I want to say a few words about this formal argument. So this is the formal argument showing that duality is true. For pure states, I've mentioned SA is equal to SAC. So these are polynomial entropies here, right? So if you replace A by AC, it follows that this is the case. Okay, but the previous section showed this is not true. Okay, here's the reason. The reason is that all algebra is not type 1. Okay? Therefore, even though the two algebras associated with A and complement commuting with each other, and in fact generate the algebra of all bounded operators on the underlying Hilbert space, these two algebras are not each other's commutant. Okay, for type 1 polynomial algebra, this will never happen. This is good exercise in the first year function analysis class. Okay? But in type 3 case, this happens precisely when the global index is greater than 1. Okay? So if you this and also another thing I should point out is that this is a formal statement. Remember, for type 1 polynomial algebras, it's all infinities. Okay? So, but what's amazing is that infinity plus infinity minus infinity minus infinity is finite. Okay? So this is a more fundamental object. Okay? Anyway, all right. So one has to be careful about formal arguments, right? But here I think the formal argument fails for a very interesting reason. Okay? All right. So yeah. So and then we also generalize this result to a much more wider context. So I want to mention this result. So motivated by this duality result, for Fermi case, this is what I proved for relative entropy. Okay. So I just, this is one of the special cases of a general formula. I just want to give you a taste of what this formula says. So if you consider conformal net, and then you got two intervals. These I prime is the complement of these intervals. You got the following formula. So let me explain what this formula is. So this is the relative entropy. Omega is usual is the vacuum state, and omega J1, omega J2 are the vacuum state restricted to J1, J2 respectively. Okay, so you got two relative entropy. C is the center charge, 8 is cross ratio. And what is this Fi? Well, Fi is some conditional expectation which plays a very important role in the study of conformal net. Okay, this is related to global index. Okay, so we got another relative entropy, and then the global index right there. Okay, so what I like about this formula is that previously I have discussed a case where we take some kind of singular limits, right? Here we got exact formula. Okay, so but of course we got three entropies here, so this is still very mysterious to me. But anyway, the duality condition sort of which motivates this identity is the case when the right-hand side is 0. Okay, but the right-hand side is never 0 as long as the global index is greater than 1. So this gives a more, I think, better understanding of the theory of duality I mentioned earlier. Okay, so let's see, yeah. So one immediate consequence of the identity proof before and the monotonicity of the corresponding relative entropy is an inequality like this, which is already quite non-trivial. Okay. Anyway, so let's see. Right. So in fact, we also proved these for full two-dimensional CFT. So for those of you who know about this, so chiral CFT is one on it's half of the full CFT, right? So if you put two chiral together, you get a full CFT, and then you can discuss similar equalities. So and it turns out the duality relation holds if and only if it's modularly invariant or the global index is 1. So Cassini and his collaborators have called such theory complete in their recent investigation of symmetries in QFT, so including generalized symmetries using operator algebra language. Anyway, so so I want to say a few words about the proof of such a relation. So maybe I should skip some. So I haven't 10 more minutes, 5 minutes. Okay, good. So maybe I should explain this to prove this result. Okay. So the proof of this result is based on investigation of how the relative entropy behaves and the decomposition of these conditional expectations So let's not worry about this one, but maybe you should pay attention to this one here. Okay. So E1, E2 inverse. Never mind about this. These are some kind of conditional expectations, but notice the right hand side is composition of these two. Okay. So you see these particular relative entropy behaves very well under compositions, right? Behaves additively under compositions under certain conditions. Okay, so this plays an important role. And so I'm going to look at the two consequences of this. So the first one is what I alluded to before. So these particular relative entropy, there's some conditions involved, behaves like logarithm of index, right? We know index is multiplicative under, sort of compositions, conditional expectation. But these behaves like logarithm, okay? But it's less equal to logarithm index, okay? So it's closely related to index, but they're not exactly the same, okay? And in some cases, one can actually show, for instance, for the conformal Nats case, if you took an interval, let the interval be getting larger and larger so that it's getting closer to the circle, you can actually recover the index, okay? So in some sense, it seems to be more refined invariant, okay, than the index we all love, right? So, but unfortunately, there are very few explicit formula for this, and I think it's a very interesting question to compute this. I have, so far the only example I know is for the bosons. Okay, there's still free series. Okay, but I think by my result, these are all fine numbers. Okay, but what are they? Even in the case bosons involve some inverse hypergeometric functions. So it's a mess, but anyway, it's a fine number. Okay. Um, anyway, so let's see. Right. So another lemma is that if you take the dual of these conditional expectations, so this is like what Hargrove did for the dual weights. Okay. So in this case, there is a similar dual conditional expectation. You find the sum of them is exact logarithm index. Okay? So this is in a special case of type 1 factors, this is what Cassini and his collaborators called entropic certainty principle. It's certainty principle because the sum of uncertainty is certain. Okay, it's always logarithm to index. Okay, so this plays a very important role in the recent work. All right, so let's see. Right. So I want to go back to that singular limits. I will finish with one more singular limit. Okay. So previously, recall what I did before, right? I got two intervals. One of the intervals getting closer to the other one, so the endpoints getting closer to touching each other. Okay. So in that case, the conformal net, if you work out the mutual information in this case, is given by this formula. Okay? So it's it's an interesting formula. As I said before, there's some very interesting underlying quantities of the conformal field theory appears. Okay, so it motivates us to consider more singular limits. Okay, so here's my recent paper, which considers a single limit of the following form in two-dimensional massive free fermion case. So this is still a free theory, but it's massive. Okay, in some sense, it's more difficult. Okay, mathematically. Okay, you don't have conformal symmetry anymore. Okay, so all the previous results apply to conformal field theory where you have extended symmetries, but now you just have the usual comparison symmetry. Okay, so there's less symmetry to use, and it's a bit more difficult. But I want to tell you what the result is. So we're going to work in two-dimensional massive free fermion theory. So this is very similar to the previous case. So I represent the double cones lie on the time equal to 0 slice. So once again, I got two intervals. Okay, so I'm going to compute these relative entropy for these two intervals. So to indicate that this depends on intervals, I have written my relative entropy. I have dropped the states, but I have just written down this, the corresponding interval. So basically, you have two intervals, B1b, CC1. B is less than C. We're going to consider the case when B is close to C in a bit. Okay, so I will consider the difference between these two relative entropies. So B1C, BC, right? So and C2C. So C and B is this is always divergent when this interval getting closer to each other. The idea is that if you let C2 goes to C, this has divergence. This one also has divergence. But it's expected this divergence of the same rate. So when you take the difference of these two divergent objects, when C too close to C plus, the hope is that you get some finite quantity out of this. Okay, very much like the mutual information or relative entropy being a finite thing coming out of the infinity plus, infinity minus, infinity minus infinity. Okay, I'll be done. Okay, in a few minutes. So in the conformal case, this function is very simple. We derived this before, but but the massive formula, this formula is highly non-trivial. So maybe I should show you this formula. So this is the final result. So we find the exact formula for this. It once again take the similar form as we had before. Two functions plus s minus. This s is not for Lyman entropy. It's what's called the regularized for Lyman entropy. It's given by the following integral. And this integral, I want to draw your attention to this integral, is the integral of what's called the tau function. Okay, this tau function studied in SJM's work back in the 70s and satisfy the following equation. Okay, this equation may not be familiar, but if you do a change of variable, it can be converted to kind of the equation of fifth degree. Okay, so that computation is it's the hardest work I have done recently. I mean, it's just a math, right? You finally have to check that you really verify the equation. But anyway, so from this you prove the C theorem in this setting. Okay, and as a consequence, we also find some similar result on tau function related tau analytic function because we related this to entropy to the spectrum of something. So it just follows trivially that this function has some analytic properties, which I couldn't find in the literature. Anyway, so yeah. So here's 3 papers where this is based on. Thank you.
Hello. Thank you for the nice talk. Are there any questions in the audience? Yes.
Yeah. Yes, absolutely, yes. So let me go back. In fact, I think I tried to set it up. But I'm not sure I did that successfully. But anyway, so yes, let's go back to yeah. So so our goal is to compute these. Our goal is to compute this relative entropy, right? So I got 2 states. I want to compute this relative entropy. So the entropies will be given by some kind of spectrum of some kind of operator. Okay, so I mean it's related to spectrum of some operator because remember it's trace roll log roll, right? So you have the diagonalized roll. So you have to find the spectrum of that roll. Okay, so that roll, remember the vacuum state is defined by Hilbert transform to some extent. Okay, so if you actually look at the finite dimensional version of that spectrum problem, you find that exactly that you have what's called the Riemann-Hilbert problem for disjoint intervals on the real line. So if you write that that spectral operator, you want to invert it, right? So you want to solve an integral equation. That integral equation, remember the underlying interval are this. So you write down that equation. That's exactly the Riemann-Hilbert problem, up to some modification. Yeah, that's for the finite dimensional system. Exactly. Yeah. There's also Riemann-Hilbert correspondence, so it's maybe a little bit confusing, but this is the Wiener-Hopf problem. Yes. Yes.
Any other question?
Okay. So it's a general principle. So if you for instance, maybe I will go So I'll go back to free fermion net. Okay, so this is how the free fermion net is defined. So this is a type 3 Lorentz factor. So let me explain this. So how is this generated? You take all those creation alienation operator, but with the psi supported on interval I. You take the polynomial algebra generated by the C size. Okay, this is a type 3 Lorentz factor. Okay, in general, it's a general principle. I think it was proved by some German guy. I forgot his name, but back in maybe even the 60s, last century. Okay, so it's based on first principle, positivity of energy, some covariance condition. So that's satisfied for any reasonable quantum field theory. It follows that the algebra of local observables is always type 3. Okay, so what I have given you is a concrete example coming from CR algebra. This is type 3 one factor. Yeah. So in other words, phenomenal entropy of this one is always infinity. But the mutual information is finite.
Any other questions? Okay, let's thank the speaker again. We have a break for around 15 minutes till the next session is at